Today we're talking about 30.3, the last little bit. We're going to talk about the standard model particle accelerators. The first is linear particle accelerators. Linear particle accelerators can only accelerate charged particles because they use electromagnetic fields. So electromagnetic fields only affect things that are positive and negative. If it's positive, it's going to go one way, and if it's negative, it'll go the other. So they won't accelerate neutrons because that's not an electromagnetic field. It has no charge. It won't interact with it. So with particle accelerators, you usually have one particle at one end, and they zip another particle and smash it into them. And this particle, whether it be a proton or a neutron, smashes into smaller particles. So you used to think that protons, neutrons, and electrons were the smallest they get. You're wrong. They actually get even smaller. Oh, except electrons. Electrons are an elementary particle. You can't smash an electron up. All right, the next is a synchrotron. It's a funny shaped particle accelerator. This one right here over here. This is a linear particle accelerator, and this one is a synchrotron where you get one particle going one way and another particle going another way, and then they open the gates and smash right in the middle. This lets you get it up to a lot faster speeds. So they use electromagnetic fields again to make sure those particles stay on the path they're supposed to stay on. So once they get these particles up to speeds and they get them to smash together, they have a couple of different ways of detecting these particles. One of them is exposing the particles on film. So they have a piece of film, and if a particle hits it, it's going to make that film exposed, so it'll be like a little tiny dot. If it's positive or negative in that electromagnetic field, it's going to cause the particles to either go this way or this way, depending on which charge it is. So it's direction. If it's neutral, it would keep going straight. And then if it gives off any light, then it's giving off a photon. So we can tell if it's a particle because we can actually see it. They also use Geiger counters. So if you get a charged particle or a gamma ray, when it reaches the Geiger counter, it's accelerated towards it and creates an avalanche of particles. So if they have a bigger particle and it hits it, it's going to spread out into lots of different particles. It makes this fancy little picture, and depending on what this picture looks like, they can detect which type of particle it is. So they find new particles by finding pictures of particle avalanches that look different than other ones. And they're like, that's a new one. What would we call that? And then the one last way they can do it is condensation trails, which there's a neat science experiment. If you look up a cloud chamber with radioactive material, like on YouTube, you can look at them. I don't have the materials to do that. But they put like a big cloud inside of a chamber, and then they do this smashing together. They have radioactive decay, and as the particles are given off, they actually leave trails in the cloud because it's water vapor, which is really super small. So these particles will move the water molecules out of the way. And so you see these little paths through the cloud. It's pretty neat. So particle accelerators help us smash what we thought was elementary particles, protons, neutrons, and electrons. And now we can smash them into things and break them up, so there's actually a lot more particles, such as pions, muons, bosons, neutrinos, all sorts of crazy things. Now, an electron can't actually be smashed up. It's a type of lepton, but protons and neutrons are made up of things. And we can use whatever protons and neutrons are made up of, put them together, and we get these pions and muons and bosons and stuff. All right, so we have something called the standard model that came from smashing all these particles up. And the standard model is trying to take electromagnetic theory, particle theory, so the wave-light concept, the hybrid, put it with the forces, which we were able to do with electromagnetism, the strong force and the weak force. We were trying to get all those together, and they work. The math says, yes, that's fine. And then along comes gravity, which is a little bit different. Every time we put it into these equations for electromagnetism and strong and weak force, it breaks down. It doesn't work. So they've been working on string theory from like the 90s into the early 2000s. That was the big thing, string theory. Each of these little particles that they're smashing into is actually a vibrating string. And if it's got a certain frequency, then it is this particular particle, or it's this, it's a proton or it's a neutron. So they've kind of moved away from that now, and they're sticking more with the particles, the standard model, saying that particles, there's a particle for every force. So, for instance, your gravitational attraction between you and the Earth is caused by the Higgs boson, right? And that the interaction of those two particles attracts you to the Earth in a way. It's more complicated than that. So there's some particles that are causing you to be attracted that way. So the standard model puts forces to particles. And this is supposed to unite gravitational relativity, relativity equations that Newton and then Einstein improved, along with electromagnetic, strong, and weak nuclear forces. So all your fundamental forces, and it mathematically joins them together to become a theory of everything. Meaning we could explain everything using this one equation, this big master equation. And in the past, we just couldn't get that to work because gravity always messed it up. All right, so now, according to the standard model, we have three sets of things. We have quarks, we have leptons, and we have bosons, which these bosons are force carriers. So let's look at the quarks first of all. The quarks tend to be a little bit more massive. We have 6 quarks, the top and bottom quark, charm and strange quark, and up and down quark. So that's the name of these quarks. They're the ones in red over here. These are actual things, the quarks. Then we have these smaller leptons. We have the tau, muon. The electron is a type of lepton, which is interesting. And then we have the tau neutrino, the muon neutrino, and the electron neutrino. So tau, muon, and electron, and then they also have neutrinos. So these are our little particles. And then we also have bosons, which are force carriers. Now, the only bosons with actual mass are the W and Z bosons. And these W and Z bosons are responsible for the weak force, which we haven't really talked about too much. I think I indicated the last time that protons turn into neutrons in beta decay. You guys remember that? Or neutrons turn into protons. I think that was what we talked about. The force that causes these is the weak force. It spontaneously happens. So that is caused by a particular force, which we call the W and Z boson. One turns protons to neutrons, the other turns neutrons to protons. And then at the bottom we have bosons, which again are force carriers that don't have any mass. You have the photon, that's your electromagnetism. Anything with electromagnetism has this photon in it, photon particle. Then we have gluons, which that is, and it sounds like glue, that holds your protons and neutrons together. That's the strong nuclear force. So everything in your body, in your atoms, are held together by this strong nuclear force. And if we didn't have that, you'd fly apart. You'd just be particles. It would be you. And then this last one, which in your book, because your book is a little bit old, is called the graviton. And that is actually the Higgs boson. So when your book was written, the graviton hadn't been found yet. It was only predicted. And the guy that put a lot of work into it and predicted it back in like the 1960s his name was Higgs. So they named it, instead of the graviton, they named it the Higgs boson after him. Because everybody thought he was crazy and realized he was right. Okay, so the Higgs boson again is a massless particle, which is kind of weird, but it's a force carrier. This gives you mass. Without it, you wouldn't exist. You have to have mass. They did find it a couple of years ago before this PowerPoint was written. That's why it says still unproven. They have evidence to show that the Higgs boson is a thing. They think they found it. It doesn't answer all their questions like they hoped it would, but it does a pretty good job at filling the hole that they had for it. So we got 6 quarks, 6 leptons, and 4 force carriers. And the W and Z boson is both the weak force. Kind of counts as force. All right, so protons and neutrons. A proton is made of 2 up quarks and 1 down quark, which obviously you saw that there's 6 different quarks. So if you put these quarks together, if you put 2 or 3 together, you're going to end up with a different type of particle. So protons happen to be 2 ups and a down. And a neutron is 2 downs and an up. Now, quarks have funny charges on them. They're either 1/3, 2/3, I think that's it. They're either 1/3 or 2/3. In order for it to become a particle, whether it's a proton or it's a neutron, their charges have to add up to be a number, a whole number, an integer. So it's either going to, when you add these up, it's either going to be -2, -1, 0, +1, or +2. If those do not work, then it will not become a particle. So you can take any of those quarks and smash them together to get them to become a particle, as long as their charge ends up being a whole number. Okay, now we have antimatter. So let's make your view of the world just a little bit wider. So we had 6 quarks, 6 leptons, and 4 5-ish force carriers. For every particle, there is an opposite particle. This is for leptons and quarks. So we have an up quark. We also have an anti-up quark because it's antimatter. So if you have an electron, the antiparticle would be a positron. It's an anti-electron. So why isn't a positron a proton? And that's because all the antimatter is the same mass but the opposite charge. So an electron and a proton are not opposite because they have different masses. A proton is matter, an electron is matter, an antiproton would be antimatter, and a positron, same mass, opposite charge. So this one up here, it says two particles have the same mass and charge magnitude, meaning that they'll either have a 1 and a negative 1 or a 2 and a negative 2, but they have to have opposite charges. So the same magnitude of charge, but the opposite charge. Whenever you get a matter and its antimatter together, so particle and its antiparticle, they will cancel each other out. And when they do that, they annihilate, meaning that they disappear and produce energy. So if you've ever watched Star Trek and they talk about antimatter engines and all of that, they're talking about putting matter and antimatter together. And when they do that, it releases energy and gives them, warp drive or whatever. And that sounds familiar, right? Turning mass into energy. That's E equals mc squared. So you can use that. Just make sure you use the mass of both the things. So if it's a proton and an antiproton that comes together, then it's the mass of both. So it would be 2m of the protons, because they both have the same mass, times c squared. Now if you're going to answer this in joules, then your mass needs to be in kilograms and this needs to be meters per second squared. But your homework recently has been asking you to answer in electron volts. So make sure you put your mass in U, multiply by 931.49, and it will give you energy in mega electron volts. All right. When they detect these particles, they can see their path of the particle. So after it smashes together, something's going to happen and it's going to do this path. So when you get a particle and it's antiparticle, you can actually see it on the picture. They look the same, but they'll be in opposite directions because they're in a magnetic field, so positive is going to go this way and negative is going to go this way. So you see a reflection of it. All right, so you guys remember we were talking about beta decay a couple days ago. This is caused by the weak force. That the beta decay was a neutron turns into a proton, and it releases an electron and an antineutrino. Well, that's caused by another fundamental force. So far we have gravity, we have electromagnetism, we have the strong force, and now we have the weak force. And this weak force turns protons into neutrons and neutrons into protons. So it is the only force that's actually caused by a particle with mass. And this W boson is released from it, and it turns into an electron and an antineutrino. So you have inside your neutron, it turns from a down to an up. And when that happens, it releases a W boson, which is just a weak force, which decays into an electron and an antineutrino. So that's what's happening even smaller than the proton. Now, it would do it the other way. A down or an up turns into a down, would release a Z boson, and you get a positron, which is an anti-electron, and a neutrino, which is the opposite of an antineutrino. So far, the Standard Model has done a really good job at connecting and unifying this electromagnetic force, weak force, strong force. And the gravitational force with this Higgs boson has finally been put in there. It seems like it's working really well. There's still a lot of unanswered questions. So the Standard Model is answering our questions, but it might not be the only thing left. There might be more to the picture. So I have, I think, 6 questions for you today. I'm not sure. Here's the first one. It says, what powers particles through a linear particle accelerator? Low. Sure. Brandon, front office.